Okay, class, we're back. Again, we're looking at the oxygen association dissociation curve. But in the last video, I ended with talking about the utilization coefficient. And I was applying it to the fact that in the tissues you have a 40, so that venous blood does have oxygen, it just doesn't have as much. Now, if you have a 40 and that's 75%, let's say, then all you do is add one more in the lungs to each hemoglobin molecule. So under usual circumstance, that's where we get into what we call the utilization coefficient for O2. The utilization coefficient equals to how much used to how much total. Generally a 1 out of 4. That's all you generally. So when you go into the veins, you really, each hemoglobin molecule is only unloading one. Okay? And that's what we call the oxygen extraction ratio, some will call too. The amount of oxygen extracted by the peripheral tissues divided by that delivered. Okay. So what we did, we loaded in the lungs and did this. Now we're going to come on the unloading aspect. The unloading. That means in the tissues. So now we're looking at in the tissues unloading. In the tissues unloading. Okay? Unloading in the tissues. All right. The way you have to look at that is this. We enter into the tissues. Okay? We enter into the tissues. Let's see if I can find something here. So here we are. Here would be the capillary. This is the arterial end of the capillary here, and here's the venule end. All right, so we're unloading down in the tissues. Now, to start with, in the capillary, these will be tissue cells. We had, let's say, a 95 to 104, okay, 95 to 104 partial pressure of O2. Then what we're going to do is, as we go through the capillary, we're going to unload that because let's look at what we have. The intracellular oxygen is around a 23. The interstitial is around a 40. So that means you would send into the interstitial fluid and then into the cell. Because remember, the cell is using O2 in the Krebs cycle to make ATP. All right, so we're unloading. Now, normally we only knock off one. Now this is how the thing is gonna go. That means that really, once you get into the capillary, you're only there a moment. You don't even need the whole length of the capillary because this unloading happens very quickly. So by the time you get just part way through, you've thrown off that one. Now this is what I want you to listen to. You still have 3 more left. You only threw off one. So under perfect situations, now this is where this comes in. Under perfect situations, if your cell has a 23, which is real good to make it. See, your cells can make it on around a 4 or 5. It was just like if we sucked all the oxygen, most of the oxygen, if we were in the classroom, we sucked most of the oxygen out, not enough to kill you, but you'd be so debilitated you couldn't do anything. So a cell can hang on with about a 3 or 4. It can hang on, but it can't do anything. So you got a lot of insurance value. All right. Now let's go through it again. So you came into the capillary, you unloaded one. If that one kept the tissue cells at 23, if that one kept the tissue cells at 23, then you go on to the venule and you're through with it. But let's say there's trouble in the tissue cells. Let's say you're exercising and you need a lot more oxygen. So this number is dropping significantly. Or let's say there's some other problem. Then what happens is you still have some ability to push more out because you still have 3 more left. You still have what? 3 more left. All right. but you're moving down the capillary, so you don't have much time. Remember, you can only unload in the capillary. So when you enter the capillary, you throw that one off. That hemoglobin throws that one off. Everything's cool if you're 23. Everything's cool. But let's say you throw that one off and you're down to, and you were at 10 and now you're at 15. Let me say it again. Let's theoretically say you threw that one off, you were at 10 because something's wrong, or you're exercising that muscle, and that one only brought you to 15, let's say, not to 23, the perfection. Then what could you do? You've got the ability to throw some more off because you got 3 left. So then before you leave the capillary, but here's the problem. You're moving down the capillary. So you need to throw the next one off much faster, hoping you get to 23, because you are moving, and if you go too far, you can't do it at all because you'll be in the vein, in the venue. So now we get to this slope issue. You see how this slope here is mild. See, that slope is mild there. What did we say about that? The more this slope is like this, the more no rate of change. That means it's real slow throwing that first one off because everything's cool. It assumes everything's cool. But if trouble is there, you're not back, then that next one needs to go off faster. That next one, see, you go in here. This remember, once I get to this, is more instantaneous. So that next one comes off faster. Then if you're still not there, the next one comes off even faster than that. So what's happening is that the reason it's changing and getting because of a vertical slope is because you need to throw it off much faster. You need to throw it off much faster because you can't throw it off after you get into the venue. So the normal utilization is just throw one off. But if trouble occurs and you're not where you need to be, then before that blood leaves that capillary, it needs to be throwing oxygen off much faster, hoping to restore the intracellular level to that. Now, I'm going to come to something else too in this one. This particular slide is saying that a tissue cell should ideally be no more than 20 to 30 micromillimeters from a capillary. So you got it. The capillaries are what supply all the tissue cells. So they need to be close to the mailboxes. The tissue cells need to be close to the mailboxes, let's say, where you're throwing stuff away. And the furthest it should ever be is 100 microns. The furthest it should ever be. Okay, and see, that's what I get into that intracellular 23 that I did in this drawing here. So kind of study that. All right, so you can kind of see now why this curve has this parabolic shape. This curve has this parabolic shape. Now, the next thing would be what makes it physiologically have this parabolic shape. Okay, and this is what we call in chemistry an allosteric effect, a site other than. Now listen to me, a site other than. All right, we're looking at the stereochemistry of the hemoglobin molecule. The stereochemistry of the hemoglobin molecule. I'm going to try to explain it this way. All right, when you throw the first one off, right here, you throw the first one off, then that collapses kind of a spot here, which is going to change the stereochemistry, the shape of this hemoglobin molecule. Now, when that occurs, it kind of opens up a spot for the second one to come off. It kind of opens up a spot, listen to me, for the second one to come off. So the second one can come off easier. So then the question is, well, why doesn't the second one go ahead and come off? Because it won't come off if the room is already crowded. Let me tell you what I mean. It won't come off. You say, what do you mean by the room already being crowded? If you are 23 and you are 40, then there's a diffusion gradient all the way down. Listen to me, a diffusion gradient all the way down. If you stay at 23, there's no room to throw another one off because the diffusion gradient would disallow it. There's no room. So you opened up that second one, ready to come off, but you can't come off because it's too crowded already. It's too crowded. However, if this is less than 23, particularly lower and lower below 23, then the room is not as crowded, the area of oxygens. So you could come and deliver that second one. That second one is perched and ready to go. It's perched and ready to go, but the room was crowded. But if you still haven't gotten back to a 23 after you threw the first one off, then there's room to discharge another one. And then there's room to discharge even the one after that if you still haven't made it. So in other words, it's that allosteric aspect of the hemoglobin molecule that causes this to happen. That allosteric is within the stereochemistry of the hemoglobin molecule that does that. Okay? So that kind of explains that. Now, we go a step further. I'm going to go a step further, and I want to get to the fact that the oxygen dissociation curve can shift. The oxygen dissociation curve can shift. Now, right here, this is a static curve. Right here, this is a static curve. But I want to talk about a curve shift. A curve shift. So we're going to start another video, and we're going to look at a curve shift and apply it to the oxygen dissociation curve. All right, thank you.